Ladies and gentlemen, welcome. This is again 4ST601 statistics in English and our seminar number 9. In our 9th seminar, we will continue in theory of probability and random variables, and we will start with probability distributions. For first time, we will start with distributions of discrete random variable, yes, because you already know that we have discrete and continuous random variables. So today we will start with discrete random variables, yes, and probability distributions. So you know probably from lessons with Mr. Hellman that we have more discrete distributions, yes, but in your seminars, yes, we will speak about binomial distribution, Poisson distribution, and hypergeometric distribution. So these three distributions are discrete, yes, and I prepared some examples for you. So we will start with the first one. We will identify what is the distribution, which distribution is it, yes, and according to these formulas we will solve it. So I think that we can start, and there you can see the first example, the first one. We have 10 fair dices, the cubes, and these 10 dices will be thrown on the table. So we have here 10 independent attempts, yes, because you have 10 dices in the hand and you will throw these dices on the table, yes. And we would like to calculate the probability that on 8 of them falls number 6, and number 6 falls no more than on 3 of them. So I will use the whiteboard and calculator, and according to formulas which you already seen, we will solve this. Okay, so there's the whiteboard, and I will write here what we know. In our situation, n is equal to 10 dices, yes, 10 dices, 10 independent attempts. And if you remember, this is the dice, yes, this is the dice, and there is, for example, the position with number 6, yes. So if you remember, when we calculated the probability that you will see this position 6, it was calculated like m divided the number of sides, yes, number of sides, yes. So our required value is 1, and this dice has 6 sides, yes. So logically, the probability that you will see this side, yes, on one dice is equal to 1 divided by 6, and we already calculated this like 0.1666 periodical, yes, 0.167 approximately, yes, is the probability that you will see this side. So we have 10 dices, 10 independent dices in this example, and we can adhere probability P that you will see the required random event on one dice, yes. So this P is 1 divided by 6. The probability that you will not see this side with position 6 is 1 minus P, and in our situation is 5 divided by 6, yes. The rest, 1 minus 1 divided by 6 is 5 divided by 6, yes. And now we can see that we have here two important parameters, n and p, and if you check your formulas, you will see that two parameters using binomial probability distribution with two parameters n and p. Yes, binomial distribution with parameters 10 and 1 divided by 6. Yes, we have here 10 independent attempts, yes, 10 dices, 10 independent dices, and the probability that you will see the random event which is required for you. So, this was our helpful calculation, so we don't need this anymore, and this image, yes, is also just illustration, yes. And if I check the example, I would like to calculate the probability that on 8 of them, 8 dices, falls number 6. So I would like to calculate probability that random variable x, number of dices on which you will see position 6, will be equal to 8, yes, 8. Okay, if you check the probability function of binomial probability distribution, yes, binomial probability distribution, you will see that there is combination number n above x, yes, times p powered by x times 1 minus p powered by n minus x. Yes? Maybe you remember from previous seminar that we already seen something like this function. You remember this situation in the case of sport shooter. Yes? Sport shooter has 5 independent shots. 1, 2, 3, 4, 5. At the biathlon, yes, and there was a question, yes, on the number of shots. Yes, do you remember? We also had n equal to 5 independent shots. Probability p 0.8. That shot will be in the target. Yes. And 1 minus p is the probability that shot will be out of the target. Do you remember this example? This example is also designed on the binomial probability distribution because we had 2 parameters. So you don't know it, but now I set this information to you that we already solved example which was designed on binomial distribution, but last week you did not know this information, yes? So now this is the same. So I will use this probability function and I will calculate probability that random variable x will be equal to 8. So in our situation this will be 10 dices above 8, yes? This will be multiplied by probability 1 divided by 6 powered by x powered by 8 times, and there is 1 minus p, 5 divided by 6, 5 divided by 6 powered by n minus x, 10 minus 8 is equal to 2. Yes? So, again, you remember from the previous seminar how can we calculate the combination number. Yes, I have here my calculator and combination number 10C, like combination 8, yes, 10 combination 8 is equal to 45, yes, 45 times 1 divided by 6 powered by 8 times 5 divided by 6 powered by 2. Okay, this probability is very, very small. 1.86 exponent minus 5. So what is it? 0.0000186, yes? Can you imagine that you have 10 dices, yes? And you will will throw on the table these 10 dice, and you require on 8 of them the same number. Yes, on 8 of them the same number. It's a very small probability that you will see 8 same numbers, and only 2 dice will be different. Yes, so this is really very small probability. If you multiply this by 100, there is 0.00186%. Yes, so this is very small probability. So we will solve B. Number 6 falls no more than on 3 of them. No more than on 3 of them. So I will delete this and I will write it that we would like to calculate probability that random variable x will be smaller or equal to 3, no more than on 3 of them. Yes. So I will be happy if I see on 0 dice value 6, or on 1 dice 0, 6, or on 2 dice 0, 6, or on 3 dice 0, 6. Yes, so maybe I will rewrite this with a little smaller font. Yes, so this will be calculated like probability of 0, or probability 1, or probability 2, or probability 3, either on 0 dice, or on 1 dice, or on 2 dice, or on 3 dice. No more than on 3 of them. Yes, so it's very important to know that we are using this probability function. So this will be deleted. Yes, and I will solve 4 probability functions. Yes, so how can we write it? 10 above 0. Yes, multiplication 1 divided by 6 powered by 0 times 5 divided by 6 powered by 10. Yes, so this will be first probability function, plus 10 above 1. Yes, multiplication 1 divided by 6 powered by 1 times 5 divided by 6 powered by 9, plus, yes, then we can continue, plus 10 above 2, multiplication 1 divided by 6 powered by 2, and 5 divided by 6 powered by 8. Yes, plus the final value 10 above 3. Yes, multiplication 1 divided by 6 powered by 3 times 5 divided by 6 powered by 7. Yes, so there is first value of the probability function, second value of the probability function, third value of the probability function, and fourth value of the probability function. Yes, so I will write the partial results. So please wait a second. 10 above 0 times 1 divided by 6 powered by 0 times 5 divided by 6 powered by 10. Okay, 0.1615. 0.1615. Yes, this result will be written here. 10 above 1 times 1 divided by 6 powered by 1 times 5 divided by 6 powered by 9. 0.3230. 0.3230. And we can continue here. 10 above 2 times 1 divided by 6 powered by 2 times 5 divided by 6 powered by 8. 0.2907. 0.2907. And finally here, 10 above 3 times 1 divided by 6 powered by 3 times 5 divided by 6 powered by 7. 0.1505. 0.1505. Okay, so we have here 4 partial results, yes, and we will calculate the summation. So 0.1615 plus 0.3230 plus 0.2907 plus 0.1505. Okay, so the result is I must delete this probability function because we don't need this function anymore. Probability that random variable x will be smaller or equal to 3 is equal to 0.9257. So this is the final result. We can interpret this in percent like 92.57%. Yes. So this is the probability that random variable x, the number of dices on which you will see value 6, will be smaller or equal to 3. So either on 0 or 1 or 2 or 3 dices, you will see position 6. And now we can continue with calculation of expected number and variance. Yes. So there is a question. Calculate the expected number of dices on cubes on which falls number 6. So we must return. Yes, we must return to our formulas. And we must find the formula for the calculation of expected value and the variance. Maybe you know that expected value in the case of theory of probability is similar to mean, yes, to average, which we calculated in the descriptive statistics. So I will use formulas. I will use the formulas and I will write here formula for the calculation of expected value of random variable x. It's calculated like n times p. In our situation, 10 dices times 1 divided by 6. The result is 10 divided by 6, and this is equal to 10 divided by 6. 1.67. So this is the expected number of dices on which you can see the value 6. Yes, expected number, the average number of dices. Yes, on which falls number 6. Yes, it can be interpreted in dices. Yes, because it's average. It's something like average, like mean. Expected value. The variance of random variable x is calculated like n times p times 1 minus p. This is the variance, yes. Okay, so 10 times 1 divided by 6 times, and there we have 1 minus p, 5 divided by 6. Yes, this is the variance, which is every time non-negative value. yes, non-negative values. So 10 divided by 6 was this result times 5 divided by 6. 1.389. 1.389. So this is the variance, which must be every time non-negative. Yes, it can be 0, but very often it's positive. Yes, and that is written because of difficult. Yes, because of difficult interpretation of variance. Calculate also the standard deviation. Standard deviation will be interpreted in basic units, so in dices. Yes. Standard deviation of random variable x is calculated like square root from the variance. So square root from 1.389. So I will use the square root from this value, and the result is 1.179. 1.179. So this is standard deviation in dices. This is variance in squared dices, but I don't know what is it dice in squares. Yes, it's not possible to interpret this value. Yes, so better is the standard deviation. So I calculate standard deviation in dices. This is also in dices. Yes? So the binomial probability distribution. And we can continue. We have here another example. At a police station, it is necessary to change 3 light bulbs in a candle. So there is a candle, yes, and 3 light bulbs need change. Yes, we have bulbs in the box, yes, hidden, for example, in the warehouse. Yes, so there is written that 30 bulbs are lying in the warehouse, but we know that 5 of them were damaged during the last police shot exercise. So we know that 5 of them, 5 light bulbs in this box, yes, with reserve light bulbs, are damaged, will not shine, yes, in the candle. We are going to the warehouse, yes, and we will select 3 light bulbs because we need to change the bulbs in the candle. Yes? So we would like to calculate the probability that we will select only dead light bulbs which were not damaged. Yes? I want to take from the box only good bulbs, yes, the bulbs which will shine in the candle, yes, not damaged light bulbs. So this is the first question. What is the probability that we will select only the light bulbs which were not damaged? And again, we'll calculate expected value and the variance. How many damaged bulbs can we expect? Yes, every time when you see the word expect or expected, yes, it's necessary to calculate expected value, the mean, yes, average number of selected light bulbs, yes, between 3 randomly selected bulbs. And of course with what variance. Because of difficult interpretation of variance, we will calculate also the standard deviation. You already know that standard deviation is square root from the variance. So we will solve this example on the whiteboard, and I will rewrite all important parameters from this example on the whiteboard. Okay, so we know, according to example, that there is a box, yes, in the warehouse, and we have here 30 bulbs, yes, in this box, and we know that we have here 5 damaged, yes, bulbs which were damaged during the police shot exercise, yes. It's necessary to take out from this box, yes, 3 light bulbs. So there is a random selection N, yes, 3 bulbs. So I will go to the warehouse I will I will select 3 boxes with bulbs, yes, from this box with the light bulbs, and I will check these light bulbs, yes. And we would like to calculate probability that random variable x, which is number of damaged light bulbs in my selection, will be equal to 0, yes. I would like to calculate probability that I will select only the light bulbs which were not damaged, yes. So, what else is necessary? We have here some numbers, yes. It's necessary to write here that capital N is equal to 30, and it's in our situation, it's a population of light bulbs, yes. The total number of light bulbs in the box, yes, in the warehouse. And there is another important characteristic, this value 5, which can be denoted capital M. Capital M is a special characteristic which is connected with our calculated probability, yes. This special characteristic is connected with this probability that random variable x, number of damaged light bulbs, will be equal to 0, yes. I have here 5 damaged, yes, and I require 0, and my random selection is 3 light bulbs, yes. If you check your formulas, you will see one important probability distribution using 3 important parameters, yes. So I will check the formulas and I can see hypergeometric distribution. Hypergeometric distribution, there is written, yes, HY, hypergeometric distribution. In different literature, you can find, for example, HG, like hypergeometric. This looks also like hydrargium, which is Latin name for mercury, I think. Yes? So we are using HY, hypergeometric distribution, with parameters capital N, capital M, and small n. In our situation, hypergeometric distribution with parameter 30, with parameter 5, and with parameter 3. And we are calculating this. So it's necessary to check the probability function from your formulas. There is a multiplication and division of 3 combination numbers. Yes, the first is capital M above x. Yes, that is the first combination number times difference capital N minus capital M. And this is above small n minus x, small n minus x, and here in denominator there is again combination number where we have capital N above small n. Yes, I hope that I rewrite this correctly. And now, because we know all parameters and we know that we are calculating x equal to 0, we will use the values, we will use the calculator, and we will solve everything. So we must calculate probability that random variable x will be equal to 0. Yes, so please use this formula and right here 5 above 0 times 30 minus 5 above 3 minus 0. This is divided by 30 above 3. Okay, so that's all, yes. I think that I can delete this part from the whiteboard, and if you have the calculator, yes, at least the high school calculator, yes, you can write directly on the display this 5C0 multiplication 25C3 divided by 30C3 and equal sign, yes? And I will see the result. Probability that random variable x will be equal to 0. I will see 5 combination 0 times 25 combination 3 divided by 30 combination 3. Enter 0.5665. 0.5665. Okay, so this is probability 56.65%. Probability that you will go to the warehouse, you will select 3 bulbs from the box, yes, and each light bulb will shine in the candle, yes. No bulb will be damaged, yes. So this is the probability, and if you remember, this was the last question. If you want to calculate, if you want to train, yes, you can calculate, for example, probability that 1 bulb from your selection will be broken, will be damaged, yes. So for practice, you can try to calculate this. Instead of 0, here will be 1, etc., etc., yes. But we would like to calculate something different. We would like to calculate expected number of light bulbs in our selection, yes. How many, yes, in average light bulbs can we expect in our selection of 3 bulbs, yes. So we would like to calculate expected value of random variable x, and according to your formulas, expected value is calculated like small n times, and there is a ratio capital M divided by capital N. So we are using our parameters. So 3 times 5 divided by 30. Am I right? Yes, 30. Okay, so this is this expected value is equal to 15 divided by 30. It's equal to 0.5, yes. Interpretation is in light bulbs, yes. Bulbs, yes, in light bulbs. So this is average. Average number, expected number of bulbs in your selection. 1/2 of broken bulb, yes. How can we understand this? I will go to the warehouse. I will select 3 light bulbs, yes. I will check these bulbs, yes, and all bulbs will be all right. I will return these bulbs back to the box, yes, and you will go to the warehouse, yes. You will select 3 light bulbs randomly from the box, from the warehouse. You will check these bulbs, and you will have 1 bulb broken and 2 bulbs all right, yes. And in average, we have 1/2 of broken bulbs. Yeah? So you can imagine it's 1/2 like this, and variance. Yes, variance. Again, variance is very complicated for interpretation. So rather, we will continue the standard deviation. Variance is calculated like n times m divided by n times, and there is 1 minus m divided by n times, and there is capital N minus small n, and here is capital N minus 1. I will check it one more time. Yes. So this is the formula for the calculation of variance. So in our situation, 3 times 5 divided by 30 times 1 minus 5 divided by 30 times 30 minus 3 divided by 30 minus 1. Yeah, so that will be the variance, equal sign, and variance will be here. Yes. So 0.5 times, that is 1 minus 5 divided by 30, enter, times, and that is 27 divided by 29. 27 divided by 29, enter. So the variance 0.3879. 3879. The variance is every time non-negative value. You can see the variance is small but positive, but we don't know what is it. Squared bulb. Yes, it's not possible to imagine. We have a bulb, squared bulb, yes, so it's difficult. So it's better to calculate standard deviation of random variable x, which is calculated like square root from 0.3879. Yes. I will delete this calculation, yes, and the result, so square root from this value is 0.6228. 0.6228. This is the deviation in bulbs. Yes, this is in bulbs, 0.6228 bulbs. Okay, so this is the hypergeometric distribution where we used 3 important parameters. Yes, so this is the difference between binomial distribution, binomial, yes, independent cases, yes, independent number of observation, n, and probability that you will see random event P, yes, hypergeometric distribution, 3 important parameters, yes, the population, yes, the large number of observation, sample, random selection, yes, and a special characteristic, yes, a special characteristic which is connected with your required probability. Yeah? So this is the difference. And we will move and we will use another distribution. I will show to you another distribution. Yes? There we have another very important example. Yes? To the small store will come 30 customers in average during 1 hour. So this is your long-term observed statistic, yes? You are the owner, for example, of this small store, yes? And you know that you can expect, yes, in average 30 customers during 1 hour, yes? Sometimes it's more, sometimes it's less, but in average, yes, you have calculated, you have expected, yes, this value, 30 customers in 1 hour. And we would like to calculate the probability. What is the probability that within 4 minutes will come to your store? Exactly 2 customers, at least 3 customers, at least 3 and at most 5. Yes? So it's very important to note that the question is not designed on this your calculated 1 hour, but on 4 minutes only. So it will be necessary to recalculate some values, some statistics in this example. And after, we will use another important probability distribution. Yes? Exactly 2, it means that random variable x will be equal to 2, exactly. At least 3, what it means? either 3 or 4 or 5 or 6 or more customers, yes, and at least 3 and at most 5, it means that you will be happy if you see 3 customers or 4 customers or 5 customers, and that's all, yes? So this is the structure of our example, and again I will rewrite everything on the whiteboard and we will solve this. Okay, so you remember that that was written that we can expect, yes, 30 customers, yes, 30 customers within 1 hour. And we know that 1 hour is equal to 60 minutes, yes? Okay, so this we know, but we would like to calculate the probability, yes, that within 4 minutes, yes, you will see, I know exactly 2 customers, yes, I will check this example here one more time, yes, exactly 2. So, we know that we can expect, yes, 0.5 customer we can expect within 1 minute. Yes, within 1 minute we can expect 1/2 of customer. So within 4 minutes you can expect 2 customers. Yes, 2 customers within 4 minutes. So this is recalculated information as from the beginning, and we don't need this first information anymore. So I will delete this, yeah, because it's not necessary for us. This is necessary. 2 customers within 4 minutes, because we would like to calculate probability that random variable x will be equal to 2, exactly to 2 customers, yes, within 4 minutes. Okay, so what we know? We know only this information. And I already said that we can, and the word expect, yes, we can expect 2 customers, yes, within 4 minutes. And we would like to calculate this probability. And because I said that we can expect these 2 customers within 4 minutes, I will check your formulas and I will find the distribution where expected value is equal to 2 customers, and this expected value is equal to parameter lambda. This is lambda, yes? Okay, and this distribution with lambda equal to expected value is Poisson distribution. Poisson distribution with parameter lambda. So we will use this Poisson distribution with lambda equal to 2 customers, expected number of customers within 4 minutes, and this Poisson distribution using probability function with Euler constant, Euler powered by minus lambda times lambda powered by x divided by x factorial. Yes, this is the probability function, and we would like to calculate probability that random variable x will be equal to 2. So probability that random variable x will be equal to 2 will be calculated like Euler constant. This is the base of the natural logarithm. Yes, if you have a calculator, I have a calculator here. Euler constant, where is E? E is here, so I will write E 2.71828, a lot of decimal places, yes, Euler constant, the base of the natural logarithm, 2.718828 and other million of decimal places. Yes? So this is Euler constant. So it's necessary to use either calculator with this Euler constant, or in Microsoft Excel you can write equal sign exponent, yes, exponent powered by 1 and enter. And you will see this Euler constant. So Euler constant powered by minus lambda times lambda powered by x powered by 2 divided by x factorial 2 factorial. So again, it's necessary to use either calculator where you have the factorial of a number, yes, this button with this sign, or there is this button with this sign, yes, okay, or in Microsoft Excel equal sign F A C T, you will open the parenthesis, you will write here this value and you will press enter. FACT returns the factorial of a number, yes? Okay, so it's easy, probability function, but you need to know how to use Euler constant and factorial of a number, yes? So this will be equal to, I will use, where is Euler constant powered by minus 2 times 4 divided by 2 and factorial, enter, 0.2707. Okay, so this is the end, this is the probability, 27.07% that random variable x, number of customers, yes, in your store will be equal to 2 within 4 minutes, yes? Okay, and we can continue with B, at least 3 customers. So we already know how to solve this, and I will delete this probability function and these parameters because we already know that our lambda is equal to 2. We are using Poisson distribution, and we would like to calculate probability that random variable x will be higher, at least 3, higher or equal to 3, yes? Okay, so you will be happy if you invite within 4 minutes 3 customers, yes? Or you will be happy if you invite within 4 minutes 4 customers, yes? And you will be happy if you invite within 4 minutes 5 customers, yes? Or you will be happy if you invite within 4 minutes 1,000 customers. I don't know the size of your store, yes, of the store, the square meters, yes, I don't know the capacity, yes, but you will be happy if you invite 1 million customers, yes, within 4 minutes, etc., etc. So we don't know where is the end, yes, we don't know the capacity, we don't know the maximum, so it will be better for us calculate this like 1 minus probability that random variable x will be smaller than 3. Yes, this will be more comfortable because this will be calculated like 1 minus probability that there will come nobody to your store minus probability that you will see 1 customer in your store minus probability that there will arrive 2 customers to to your store, yes? 3 is already acceptable, so this is the end, yes? So it's necessary to calculate 3 probability functions, yes? So I will clean this part of the whiteboard, yes? Okay, this will be deleted. And we will solve 2 probability functions. So there will be probability that random variable x will be equal to 0, probability that random variable x will be equal to 1, and probability that random variable x will be equal to 2. Okay, here, here, and here. Yes, 3 probability functions. So, Euler powered by minus lambda, yes, times lambda powered by x divided by x factorial, yes. So this will be the first probability function. Second one, Euler powered by minus lambda times lambda powered by 1 divided by 1 factorial. So this will be second probability function, and here Euler powered by minus lambda times lambda powered by x divided by x factorial. Okay, I don't know, yes, I have here already calculated this probability because we already calculated this. So I will delete this part from the whiteboard and I will write here the result. So please wait a second. Okay, so this is equal to 0.2707. 2707, yes? And here, for example, Euler, where's Euler? Here, powered by minus lambda times 2 powered by 0 divided by 0 factorial, enter 0.1353. 0.1353. Okay, and here Euler powered by minus lambda times lambda powered by 1 divided by 1 factorial, enter 0.2707. 0.2707, yeah, the same result like here. Okay, so we have 3 results, and now 1 minus probability 0.1353, yes, 0.1353 minus 0.2707 minus 0.2707. Okay, so result 1 minus 0.1353 minus 0.2707 minus 0.2707. Enter 0.3233. 0.3233. Yes, so this is the probability that random variable x will be higher or equal to 3. Yes, we calculated this like 1 minus probability that x will be smaller than 3. So 1 minus 0 or 1 or 2 customers in your store. Yes, so this is the calculated result. And of course, we have here C, at least 3 and at most 5, yes? At least 3 and at most 5. So this will be calculated like x will be higher or equal than 3 and smaller or equal to 5, yes? At least 3, at most 5. So this will be summation that random variable x will be equal to 3, 4, and 5. Yes, summation of 3 probability functions. So I will delete this. I don't have calculated any of this value, so we can solve it here. Yes, so I will delete this and we will calculate probability that random variable x will be equal to 3, like Euler powered by minus lambda times lambda powered by 3 divided by 3 factorial. Yes, this will be the first important part, and we can continue probability that random variable x will be equal to 4 Euler powered by minus lambda times lambda powered by 4 divided by 4 factorial. This will be the second result, yes. And finally, probability that random variable x will be equal to 5. This will be calculated like Euler powered by minus lambda times lambda powered by 5 divided by 5 factorial. Yes, so this is the last calculation, and I can start with this. Euler powered by minus lambda times lambda powered by 3 divided by 3 factorial. 0.1804. 0.1804 here. Euler powered by minus lambda times 2 powered by 4 divided by 4 factorial is equal to 0.0902. 0.902. Okay, and finally this one, Euler powered by minus lambda times 2 powered by 5 divided by 5 factorial. 0.0361. 0.0361. Okay, so these 3 values, yes, you can calculate the summation, and the result of this will be written, for example, here 0.1804 plus 0.0902 plus 0.0361. Result is 0.3067. 0.3067. So this is the probability, 30.67%. Yes, that within 4 minutes, yes, there will arrive either 3 or 4 or 5 customers to your store. Yes. There is not question about expected value and variance, but we already said that expected value of this probability distribution is parameter lambda. Yes, expected value in this case is parameter lambda. So in our situation, 2 customers. Variance of this distribution is again lambda, so 2, but I don't know what is 2 customers in squares, yes? So it's also possible to calculate standard deviation of random variable x, like square root from 2, and the standard deviation square root from 2 is equal to 1.414. 1.414. So this is calculated the standard deviation. So that's all. We have here another example. In a big population of 10,000 people, there are 100 people left-handed, yes. So you can imagine a small town, yes, with 10,000 inhabitants, and there are 100 people left-handed in this small town. If we randomly select 50 persons without returning, we would like to calculate probabilities. Yes? So we have here three important information in the text of this example. A population of 10,000 people, so the number of inhabitants, for example, in a small town. Yes? A special characteristic that the person is left-handed. And random selection from this population, from these inhabitants, yes, 50, without returning. And we are calculating the probability that there are among them nobody left-handed. So we would like to calculate probability that random variable x, number of left-handed persons in our selection, will be equal to 0, because a special characteristic is that the person, yes, is left-handed. Exactly three left-handed. So we would like to calculate probability that random variable x will be equal to 3. Yes, so there is probability that random variable x will be equal to 0. Probability that random variable x will be equal to 3 and at least 3 left-handed. So this will be probability that random variable x will be equal to 3 or 4 or 5 or 6, etc. So for us it will be better to use 1 minus the rest. Yes, 1 minus probability that we will select nobody left-handed person, or 1 left-handed person, or 2 left-handed persons, yes? Because 3 is already here, at least 3. So 1 minus P0, P1, P2. So we know how to solve this, and because this example is a specific, I will show to you approximation. I will show you approximation. You already know that we can use hypergeometric distribution, because we already use hypergeometric distribution, and you know that we have here three important parameters. But this example is very large, with large numbers, large values. It will be complicated to solve this on calculator, so I will show to you also approximation of hypergeometric distribution by another distributions, binomial and Poisson. So it will be good to use the whiteboard and write first steps on the whiteboard. Okay, so do you remember the conditions from example? There was written that we have a population of 10,000 inhabitants, yes, a small town. There is a special characteristic which can be denoted by capital M equal to 100. Yes, we have 100 left-handed persons, yes. And random selection n is equal to 50 persons. So according to this, yes, we can expect that this is case of hypergeometric distribution with parameters n, m, and small n, yes, and we can calculate the probabilities, yes, according to this probability function. I will use the formulas, yes, and in formulas we have capital M above x, yes, the first combination number times. There is capital N minus capital M minus capital M divided by, and there is small n minus x. Am I right? Yes. And in denominator there is capital N above small n. So this is the probability function, and we already know that we would like to calculate a probability that random variable x will be equal to 0, yes, nobody left-handed. And probability B, we would like to calculate probability that random variable x will be equal to 3, am I right? I will check it here in my Excel. Yes, exactly 3 left-handed persons. And probability C is probability that random variable x will be higher or equal to 3, at least 3 left-handed persons. So in our situation 1 minus probability that there will be nobody left-handed, minus probability that there will be 1 left-handed person, minus probability that there will be 2 left-handed persons. Yeah? So this is our A, B, and C. Okay, so if I use, for example, this formula as for the calculation of A, as you can try to use here values. What was here? Capital M, 100, yes, above 0 times there was a difference. 10,000 minus 100, yes, above small n, 50 minus 0. Yes, this is divided by, and there is 10,000 above small n, so 50. Yes. Okay, so you can see that we have here large combination numbers. 100 C0 multiplication 9,900 C50 divided by 9,900 C50. Okay, so I have a calculator in my hand and I will try it. Yes, I will try to write here 100 combination number 0 times 9900 combination number 50 divided by 9900 combination number 50. Enter. And there is a mathematical error. Why is here mathematical error? Because this calculator does not have enough memory for the calculation of this. Yes, it's very large number, yes, with exponent more than 100. So there is not enough memory in the calculator for solving this example. Yes? So we know that we have Excel. So there is one option to solve everything in Excel, because Excel has enough memory, yes, and your computer has enough memory for calculation this, or we can use approximation. I will show to you both ways. Either Microsoft Excel or approximation, yes? So, I will delete this, yes? And I show to you how can we approximate this distribution by another distribution, and I can show to you how to solve this on calculator if you have not enough memory, yes? So, can you see these three parameters? We can calculate the ratio. We can calculate ratio 100 divided by 10,000, and this ratio will be capital N divided by capital N. Yes. In our situation, the result 100 divided by 10,000 is equal to 0.01. Yes, and this can be denoted like P. Why P? P, because this is the probability that we will randomly select a left-handed person. Yes, there is a population. There is all possible cases. Then we have all possible cases. Yes, and there is number of left-handed persons. So this is the probability that randomly select person from the population will be left-handed. Yes, and we have n equal to 50. So 50 independent attempts. Yes. Can you see these two parameters? I will not use these parameters anymore. Yes. I reduce 3 parameters to 2 parameters, and I will use binomial distribution with parameters 50 and 0.01. Yes. So instead of hypergeometric distribution, I will use binomial distribution, and I will try to calculate, for example, this probability that random variable x will be equal to 0. Yes. Do you remember the probability function n above x? Yes. Times p powered by x times 1 minus p powered by n minus x. Yes, this is the probability function, and instead of these values, I will use directly our parameters. Yes, so n50 above 0. Yes, times 0.01, this is times 0.01 powered by 0 times 0.99 powered by 50. Try to calculate this. Yes, try to calculate this. The result is 0.99 powered by 50, and this is equal to 0.6050. 6050. So there we have calculated 60.50% probability that we will select nobody left-handed. Yes, there will be no left-handed person in our selection, as if we select 50 persons from the population. Yes, I used binomial distribution instead of hypergeometric, and I will show to you the proof that we have almost a similar result. Yes, I will show this to you in Microsoft Excel. Okay, and we can continue. I can delete this. Yes, I can delete this, and we can continue with approximation. Do you know the expected value of binomial distribution? Binomial distribution has expected value equal to n times p. Yes? So this is expected value of binomial distribution. In our situation, 50 times 0.01. Do you know how many is 50 times 0.01? 0.5. 0.5. Okay. So this is expected value, and which other distribution using expected value equal to some number, Poisson distribution. We know that we have a Poisson distribution with parameter lambda, and in the case of Poisson distribution, expected value is equal to lambda. So now we will try to use Poisson distribution with parameter lambda equal to 0.5, and I will try to solve everything using Poisson distribution. So now I don't have these parameters anymore. Yes, and I don't have these parameters for the binomial distribution anymore. Yes, and I will try to solve everything using Poisson distribution. So for example, again, this one. Yes, we know that probability function is equal to Euler powered by minus lambda times lambda powered by x divided by x factorial. In our situation, probability that random variable x will be equal to 0 will be equal to Euler constant powered by minus 0.5 multiplication lambda 0.5 powered by x powered by 0 divided by 0 factorial. Okay, so you are able to solve this. Where is Euler? Here, powered by minus 0.5 times 0.5 powered by 0 divided by 0 factorial. 0.6065. 0.6065. Okay, do you remember the case of binomial distribution? In the case of binomial distribution, we had here 0.6060 or 6050. Yes, so there is small difference, but in some specific situation, the small difference is not significant for us because we need to solve example. Yes. And you can see that I have a large, expensive calculator, but exponent higher than 100, yes? It's not possible to solve in this example, so I was not able to solve these probabilities with hypergeometric distribution, yes? I used Poisson and hypergeometric. And now I will show to you everything A, B and C in Microsoft Excel using hypergeometric distribution, binomial distribution and Poisson distribution. Okay, so I hope that I will be able to solve everything here on this field. Yes, there is only a screenshot of hypergeometric distribution because the hypergeometric distribution is only one where I am able to do mistake because there is a lot of letters, yes, and if you are nervous you can do the mistake, yes. I believe that I am able to remember binomial distribution and Poisson distribution, yes, but hypergeometric is a little bit more complicated. So there is a screen, yes, with our example, and it will be good to create here a small statistical table. So I will write here random variable x, yes, random variable x. And we know that we must calculate probability that random variable x will be equal to small x. Yes, and for our purposes, we need x equal to 0, 1, 2, 3. Yes, 0, 1, 2, 3. And finally, we must calculate 1 minus P0 minus P1 minus P2. Yes. Wait a second. Okay, I will use this alignment. Okay. Why? Because nobody left-handed will be probability that random variable x will be equal to 0, yes? Exactly 3 left-handed will be probability that random variable x will be equal to 3, and at least 3 left-handed we will calculate like it was written here on the bottom part of the whiteboard, like 1 minus P0 minus P1 minus P2. Yes, so we need to know these three probabilities. Yes, and here we will calculate probability that random variable x will be equal to x. And we will start with hypergeometric distribution. Yes, hypergeometric distribution will be the first one. What we need? We need to know parameter n. Yes, we need to know parameter n, which will be equal to 10, 0, 0, 0, 10,000. Yes. Can you see here I have a parameter n. N is equal to 10,000. Yes. Another important parameter which will be used in our calculation, capital M. Yes. Capital M is equal. I will use alignment. Yes, and that will be 100 left, bold. This will be also bold and yellow. Yes. So this will be another important thing for us. Okay, and small n. Yes. The sample size, random selection. Yes, our random selection is equal to 50. Okay, and 50 will be here. So, can you see this table with parameters? Yes, for hypergeometric distribution, and there is a formula for hypergeometric distribution. So, I think that we can start with calculation. So please, right here, equal sign and the function is combine. Returns the number of combinations for a given number of items. Yes, equal sign combine. So we'll open the parentheses, or you can double click on this function, and there we have a number and number of chosen. Yes, the number is capital M. And we must use function for, because capital M is parameter, yes? So it must be fixed. So please use this dollars function for, yes? Okay, and the number of chosen is x, and x is a variable. So this will not be fixed, yes? You see that I did not use dollars. Multiplication, and another combination number. So please write combine. Open the parenthesis and open the parenthesis because there is a difference. There is difference capital N, which must be fixed. Please use dollars minus capital M 100, which must be fixed. Please use dollars. Yes. So this is the first part from this combination number, and this is above. So comma. Yes, and below is small n minus x. Small n is parameter, so it will be fixed, and x is variable, it will not be fixed. Please right here is comma and open parenthesis, and this difference, small n, 50, function for minus small x, x is 0. Close parenthesis and close parenthesis of combine function divided by, and what is in denominator? Another combination number. So capital N above small n. So both parameters, so both values will be fixed by function for by dollars. Okay, so divide it, combine. Open the parenthesis, and there is capital N, function 4, comma, and n, 50, function 4, close parenthesis. And now please click enter, and you will see the result. So please, I hope that everything is alright. Yes, you can see we will use only for decimals. and it's possible to calculate it to the end. So this is the probability that random variable x will be equal to 0. Nobody left-handed in your selection. If you remember, we already calculated the 0 for case of binomial distribution and for case of Poisson distribution. So we will use these parameters and we will try to calculate approximation here in Microsoft Excel. So there will be binomial distribution. I will use formatting. Probability that random variable x will be equal to x will be here. I don't need this probability function anymore, but it's necessary to use probability function of binomial distribution n above x times p powered by x times 1 minus p powered by n minus x. I remember this formula, yes? So we will calculate this, but we need to know parameter p. Parameter p will be calculated, for example, here, p. Yes, parameter p is equal to, wait a second, copy format, here, and parameter p is calculated like capital M divided by capital N, yes? Do you remember? And the result is 0.01. Okay, so do this. Please do this. There is our parameter, alignment yellow bold, okay? And here we will solve this. I will use also this formatting, equal sign, combination number, combine, yes? And what is here in combination number? N above x, small n above x. N is parameter, x is variable. So what will be fixed by function 4? N will be fixed by function 4 above x. X is a variable, so this is combination number times. And we have here p powered by, but p is again fixed because this probability is still the same, yes? You can see dollars. Power function, the hat. I am using left out 94, yes, combination on the numerical keyboard, but you can find this hat function, for example, on button 6, English keyboard, yes, button 6, using shift. So please write here the hat, the power function. Can you see hat? This is powered by x, and x is variable, yes, times, and in parentheses we have 1 minus probability p, and p is again fixed, yes, you can see dollars, so everything what is fixed are parameters, and what is not fixed is variable, yes, variable x, okay, and this is powered by n minus x. Small n minus x, and n is parameter, so please do this. Again, power function powered by n50 fixed, yes, minus x. X is variable, close. Okay, so you can see this formula, it's very easy. So please click on enter. Enter, and you can copy these formulas to the end. Maybe you have a question. If I give you this sheet, solved sheet to you, no. You have infinity times and infinity options for watch this seminar. So if you are not able to write it on the display of your notebook, you have infinity options to repeat it, so please calculate it at home, yes? I will not provide to you this solved Excel. You can pause this video and watch it, yes? So please try to train, you will need it, yes? Okay, so there is my result, which I already showed to you on the whiteboard, yes? So you can see it's the same. And there is very small difference between this value and this value. So this is response A, exactly 3. This is response B. 1.2%, 1.2%, yes, we have here the same results. C will be calculated at the end here, yes. So this is a situation of binomial distribution, and finally you remember that we used Poisson distribution. Yes, Poisson distribution needs parameter lambda, yes, parameter lambda, and this lambda will be equal to, I will use bold, yellow, right alignment, and here will be calculated lambda. How can you calculate lambda? Like multiplication n and p, yes? N and p will be lambda, expected value for the Poisson distribution, yes? So n times p, enter, and the lambda is 0.5, yes? Okay, so there will be Poisson distribution, formatting, probability, okay? And here we will start with writing of probability function of Poisson distribution. Do you remember Poisson probability function? Euler constant powered by minus lambda times lambda powered by x divided by x factorial. So I will do this. I will write it here. I will use this formatting here, and we will start here, equal sign. Euler constant is exponent, yes. You can see there is returns e raised to the power of a given number, exponent, yes, exponent, open the parenthesis, exponent powered by minus lambda. Lambda must be fixed, can you see dollars, yes, times, what is now lambda, powered by x, yes, so times lambda, lambda will be fixed. Yes, so again function 4, power function, the hat, yes, powered by x, and this is divided by factorial of x. Do you remember the function which I wrote for you on the whiteboard? FACT returns the factorial, FACT returns the factorial of a number, factorial of x. Close the parenthesis. Can you see what is parameter and what is variable? So please click on enter. And you can see that we have here again the similar results. Yes? Hypergeometric distribution in this situation was not able to solve, yes, to produce on the calculator. So we used binomial and Poisson on calculator for obtaining the results, yes? And you can see the differences are not significant, yes? We will solve also this. We will solve also this. Equal sign like 1 minus probability 0 minus probability 1 minus probability 2, and there will be the response. There will be a response C. Yeah, so I will use, for example, orange, and orange. Yes, and you can see that there is A, there is B, and there is C. Yes, 1.35%, 1.38%. 1.44%, yes, is a response at least 3 left-handed persons in your selection. So I showed to you approximation of hypergeometric distribution by binomial distribution and approximation of binomial distribution by Poisson distribution, yes. This is possible to use if we have large samples, yes, n at least 30, and capital N, the population. If this population is higher and higher and higher, more, yes, than 10,000, for example, 100,000, 1 million, etc., higher and higher and higher, these values are more and more and more similar. Yes, more and more similar. If this population is higher and n is at least 30 observation, yes, so everything is all right. Yes, you can see that differences are not significant and you know how to approximate the distributions. Okay, so that's all for today. This is the end of seminar number 9. Next week we will start with continuous probability distribution. So I hope that everything was clear. Have a nice day, bye bye, and I hope that I will see you next week.